All right, everybody, welcome back. So now that you know how to do a single factor exploratory factor analysis for seeing how much each item relates to a single hypothesized factor, you have to think exploratory factor analysis as a method for dimensionality reduction. In the context of measure development, we think of this as figuring out how many unobservable factors are represented by the items on the measure itself. In a truly exploratory situation, you may not know which factors the items on your measure are related to, or even how many factors are represented by the items on your measure. And take a look at this figure here. Behind the scenes, this is our final result in terms of what does it look like when items cluster with one another to create these different dimensions. And for this specific tutorial, we're going to switch things up a bit. We're going to use the Big Five inventory. This is the BFI data set from the Psych package. So there's 25 personality self-report items that are taken from the International Personality Item Pool, and they were included as part of the Synthetic Aperture Personality Assessment. And this was a web-based personality assessment project. The data is from 2,800 subjects, and they're included here as a demonstration set for scale construction, factor analysis, item response theory. So this is going to be really good for us to practice with factor analysis. There's also 3 additional demographic variables: sex, education, and age. In this data set, we're not going to use those. The item data here were collected using a 6-point response scale, going from 1 very inaccurate, 2 moderately inaccurate, 3 slightly inaccurate, 4 slightly accurate, 5 moderately accurate, and 6 very accurate. 5 questions measure each of the big 5 personality traits, which are extroversion, agreeableness, openness, conscientiousness, and neuroticism. These are known as the Big Five traits. They've been extensively studied and they're agreed upon by many personality researchers. And the BFI dataset in the Psych package includes 3 demographic variables. And since your analyses only work with item response data, again, we're going to remove these items. Though we clearly already know the scientific theory behind this measure and the data set, let's imagine that we don't have this information just for the purpose of learning how to run an exploratory factor analysis with multi-dimensions. So you'll use the head function to look at the first rows of data. This is after you load in the Psych package and you load in the data set and name it. You'll also notice that the column names each consist of a number and a letter. These indicate the personality trait that the item is hypothesized to measure and the question number. For example, A1 is the first question for the agreeableness trait. C1 is the first question for the conscientiousness trait, etc. If you remember from the first tutorial, we were going to use the same data set for both exploratory and confirmatory analyses. Thus, it's really important to split your data. And here's why. Using the same data set for both will result in overfitting. So we're going to use the same splitting strategy as before. And here, you'll use 1/2 for the data for the EFA and the second half for the CFA. In practice, if you have a sufficient sample size, you're going to want to use this method. However, it is acceptable to not have to use this method and only use the same data set for exploratory factor analyses. But remember, it's going to result in overfitting, and there's going to be some degree of bias in there. We're going to split the data set and we're going to check it to make sure it's 2 distinct halves. So before this, go back over the code. We're just saying count the number of rows in the BFI data set and name it N so we can call back on it later. Then we need to create another object called indices. And what we're doing is we're saying that's going to be a sequence from 1 to the number of rows in the BFI data set, which would be 2,800. Then what we're going to do is we're going to start creating our EFA and our CFA split data sets. The first one, we need to take a random sample. And what we're going to do is we're going to take it from indices, which we created here. In other words, all the items. Floor, just think about it as a lower estimate, but here we're going to take the data set and cut it in half. So in other words, half of these values, and we're going to store it in the EFA. This last one, what this is saying is that from indices, this object, take a subset. And that's what the brackets are for. And we're going to take a subset of everything that is not, that's the exclamation point, everything that's not from indices, that's in indices underscore EFA already. In other words, the rest of the items that we didn't take yet. We're going to use those indices to split the data set, which you already did here. And again, open brackets takes a subset of your data. So I'm saying from the BFI data set, use the items that we pulled out from EFA. Comma space means If you remember, rows by columns. So we're calling on those rows, we're calling on the people. And then we're doing the same thing for the CFA data set. Like I said, to make sure that we split it properly, we're going to verify with the head function. And this is an empirical approach to dimensionality. Now, although we know that the theorized factors for the BFI data set are made up of 5, you may not always have a theory to guide your analysis. So in the absence of theory, you're going to use an empirical approach to quantify dimensionality. And to figure out the number of factors the items represent, you're going to look at the eigenvalues. And if you remember, the eigenvalues are just a way of quantifying the unique factors within that correlation matrix. And we're going to work through an applied example of using eigenvalues. So they're calculated from matrices. So our first step is to calculate the correlation matrix. I want you to notice that we're using the half of the data set that we separated out for EFA. Also, the correlation matrix is calculated using observations that are what's called pairwise complete. In other words, no missing data. Once you've got the correlation matrix, you're going to use it with the eigenfunction to calculate the eigenvalues. And the result is a list object containing several pieces of information. You're going to check out the values in the elements to view the eigenvalues. And a general rule is that eigenvalues greater than 1 represent meaningful factors. And you can count these values in the results, but there's also a quick way to visualize the information. We're going to visualize the eigenvalues with the scree plot using the scree function on that correlation matrix that we created here. You'll get an output like this, and it's complete with a horizontal line to help you count the values that are greater than 1. So let's move on to our tutorial in R. Okay, everyone, now we're going to use the BFI data set in R. Again, this is going to be 25 items that we're going to look at to measure the big 5 personality traits. We're going to trim it down as well to only use the item responses that are available. And since we'll be doing both exploratory and confirmatory factor analysis, we're going to start out by splitting our data set. So we're going to use the same process that we did before with the GCBS data set in the unidimensional exercises. So first thing, we're going to load in our data set from the psych package, and we're also going to name it BFI, and then we're going to look at the first couple observations. Here we go. Notice it's stored in our environment. Then here, because if you recall, we have sex, education, and age variables also in this data set. That's not going to work for the purposes of factor analysis. Remember, we're only looking at items to develop our constructs. Therefore, I'm going to remove it. And this is pretty simple. All I'm saying here is from the BFI data set, run this function from the package dplyr called select. And in select, we're going to only take out variables that we want. What's nice is I don't want to write 25 different variables. So using the select function, I can just remove age, education, and gender by putting a minus sign in front of each variable. This arrow says, once you're done with all these operations, name it the BFI data set again. And notice this has 28 variables here, 2,800 observations. I am going to run this function, and notice we got rid of the 3 variables. I can get the names to make sure everything works down here. Great. Now I'm going to establish 2 sets of indices to split my data set. Remember, this is just counting the number of rows in the BFI data set, which is 2,800, and storing it. And when I do that, it gives it a value of 2,800. Then I'm going to create something called indices, and it's going to be a sequence of numbers from 1 till 2,800. See that right there? So we have all our indices. We need those indices to take from our data sets. So here, we're going to take the first ones for EFA. And I'm saying take a random sample from these indices, so any one of these, by taking half of it, half of the n. So half of 2,800 is 1,400. So in other words, I want a random sample of 1,400 variables to put in my EFA. Here, I'm doing the same process, except I'm not taking a random sample because we still have 1,400 left over from the other one. So what we're doing is I'm saying from indices, take anything that's not from indices in the EFA data set. In other words, the leftovers. And now I have a CFA data set from 1 to 1,400. We always want to make sure that those indices split into 2 halves really nicely. So let's make sure they're distinct. Great. And just to let you know what these 2 lines of code did, I said, take from the BFI data set the indices that we created for EFA and put it in this new EFA data set. Do the same thing for CFA. Now we're going to calculate the correlation matrix. And this is to empirically determine the dimensionality of our data. This is a common strategy to examine the eigenvalues, because eigenvalues, if you recall, are numeric representations of the amount of variance explained by each factor or component. And eigenvalues are calculated from a correlation matrix. So we're going to need to use the core function to calculate and store the data set's correlation matrix before calculating our eigenvalues. You'll need to specify that you want to use pairwise complete observations, and the default is just to use everything. But if your data set has any missing values, this is going to leave you with a matrix full of NAs. So you'll do these calculations in the BFI underscore EFA dataset that we just created. So let's start off, and we get a nice correlation matrix. Everything ran nicely. Next, I want to use the correlation matrix to calculate eigenvalues. So do that here. I'm going to store it in something called eigenvals. And this is going to be the ones for EFA. Run that. We're good. Now I want to make sure everything went well. So I'm going to look at them. And all I'm saying is from this object that we stored, eigenvals right here. It's a list of 2. I'm just taking the values of them just so I can view all of them. And there should be 25 items. Now I'm going to look at scree plots for EFA. This is nice because EFA tells us 1, 2, 3, 4, 5, 6, which is one greater than what we know in the literature. We're going to finish this example after the next part of the lecture. So now that you're working with multidimensional data, we have to think, what does this even mean? What do the number of factors tell you? And why are you getting conflicting information from theory and the empirical analyses? Let's remember that factors are constructs. The answers are in the relationship of theory to statistics. A construct is a hypothesized attribute that cannot be directly observed or measured. Some examples of commonly studied constructs include self-determination, reasoning ability, and extroversion. Typically, measures are designed to measure specific constructs. While constructs are theory-driven, factors are their mathematical counterparts. Each factor corresponds to a construct. When you conduct a confirmatory analysis, you evaluate the strength of the hypothesized relationships between items and the constructs they were designed to measure. Model fit statistics provide information about how well the hypothesis fits the data, and factor loadings quantify the relationships between items and constructs for reporting and interpretability. When you conduct a confirmatory analysis, you evaluate the strength of the hypothesized relationships between items and the constructs they were designed to measure. Model fit statistics provide information about how well the hypothesis fits the data, and factor loadings quantify the relationships between items and constructs for reporting and interpretability. Let's talk a little bit more about this. Without theory, you conduct exploratory analyses guided by mathematical values like eigenvalues. You continue the exploration by running multidimensional EFAs to see how the items relate to each of those factors. While all of this information can be very helpful, like in a situation where you don't know much about your data, a lack of theoretical grounding can actually make these results very difficult to interpret. You can make an educated guess from the factor loadings resulting from your EFA, but this can be challenging. So running a multidimensional EFA works just like a unidimensional EFA. All that you have to change is the N factors argument. In the exercises in R, we're going to go through the number of factors recommended from the scree plot, which was 6. As you remember, the theory behind the data set recommended 5 factors. I'll discuss this disagreement in more detail later and offer some empirical ways to compare different models. Remember, to view a summary of results from the model object, all you have to do is enter the model object on its own line. No need to use the summary argument. I prefer using the print statement so that the reader knows, or whoever's going to work with your code knows what exactly you're doing. They may not be well versed in R. This would be helpful for them. As before, you'll be interested in the factor loadings, which represent each item's relationship to each underlying construct. However, the factor loadings look pretty different for a multi-dimensional EFA. Here are the loadings for the first 15 items. As you can see, the 6 factors are represented by the 6 columns. You'll notice the factors have been assigned arbitrary names and that they're not in the order you'd expect. This is due to the rotation that happens during the mathematical process behind a multi-dimensional EFA. You'll also notice that some item factor pairings don't have loadings. The results automatically exclude negligible factor loadings for ease of interpretation. Now, interpreting interpreting these loadings can be very challenging. Unlike a CFA, the factors don't have assigned meanings, so the user is left to infer these meanings based on the patterns of item loadings. For example, we can guess that factor MR5 is closely related to agreeableness since the A items all have strong relationships. We can also guess that item A1 should be inversely scored due to its negative relationship with the factor. Individual factor scores are also different. Rather than a single factor score, each person now has a factor score that's estimated for each of the 6 factors. And like before, any missing data means that the factor scores will not be estimated, as we see with person 65237. These factor scores should be interpreted until you have a good working hypothesis for what each of the factors in your EFA represents. Once you have that hypothesis, you can make inferences about the constructs. Now we're going to go back to our tutorial on how to run a multidimensional EFA. Now that you've examined the eigenvalues and scree plot to find the data-driven recommended number of factors, you can get down to actually running the multidimensional EFA. So remember before when we ran it as a unidimensional EFA using the FA function? To run a multidimensional EFA, you're going to want to use the n factors argument to specify the number of factors desired. Just like the previous exercises, you're going to want to be sure to run this analysis on the BFI_EFA data set from earlier. So here I'm going to run this. Now you could say you ran a multidimensional EFA. Now, as before, you'll be interested in items' factor loadings and individuals' factor scores. These will be interpreted in the same way, but since your EFA is multidimensional, you'll get results for each factor. Remember, an item's loadings represent the amount of information it provides for each factor. Its meaningful loadings will be displayed in the output. You'll notice that many items load onto more than one factor, which means they provide information about multiple factors. This may not be desirable for measure development, so some researchers consider only the strongest loading for each item. Each examinee will have a factor score for each factor so that the matrix won't include the blanks. However, examinees with missing data will receive NA scores on all factors. So let's look at the item's loadings now. If you notice, there's some high loadings on here. Anything above 0.3 in terms of absolute value is considered an acceptable loading. We're looking for unique structures. It looks like only this item loaded poorly for factor 2. There we go. Looks like for all the A's, so for agreeableness, it's factor 5. All the C's for conscientiousness is factor 3. And then now we're going to use the head function to look at the first few rows of examinees' factor scores, which are stored in the scores list element. Let's run this code. Very nice. We've now got the most important pieces of information for our EFA. Now that we can run multidimensional EFAs, we need to learn how to interpret various model fit statistics. When thinking about model fit, there are 2 types of different fit statistics you should consider. There's absolute fit statistics, and those are useful for making a judgment about whether or not a model fits adequately. These fit statistics have set ranges and meanings, and they have established cutoff values that are commonly used to determine whether or not a model has good fit. Some examples include the chi-square test, TLI, and RMSEA. From class, I brought up a couple others like CFI and SRMR. We also have relative fit statistics that have set ranges or meanings. They're only useful when comparing nested models estimated from the same data set. Here, we're just going to focus on BIC, but you can also use the AIC. And when it comes down to it, all of the absolute fit statistics attempt to quantify the discrepancy between the observed data and the data that would be expected given the model. These 3 common fit statistics represent the difference on different scales and are calculated very differently. Ideally, the chi-square test would have a non-significant result, meaning the observed and expected data are not significantly different. However, since the value of this test is affected by sample size, this rarely occurs for large data sets. Both TLI and RMSEA range from 0 to 1. The Tucker-Lewis index is also known as the penalized non-normal fit index, meaning that more complex models are penalized for adding additional parameters. This can be roughly understood as how well the observed data match the expected data. Larger TLI values are better, and a model can be considered to have good fit if the value is greater than 0.90. RMSEA, otherwise known as the root mean mean square error approximation quantifies the differences between the observed and expected data. RMSEA values are interpreted in the opposite direction as TLI values. Smaller values are preferred. And here we're looking at values less than 0.05 that are said to indicate good fit in practice. All the fit statistics discussed are displayed in your model output. And as you see, when you run a multidimensional EFA on the BFI EFA dataset with 6 factors, check out our chi-square value. We get a chi-square value that's extremely high, 10,012.06. And that is significantly different from 0 based on the p-value. This definitely isn't ideal, but it's unsurprising given the sample size. You can also see that the TLI value is 0.922, which is above the cutoff, and the RMSEA is at 0.042, which is below the cutoff. These are good values that indicate that the model adequately fits the data. You'll notice that these values also contain the BIC value for this model, which is negative 614.5. However, since relative fit statistics don't have any value when they're isolated, this doesn't mean much to us just yet. To use relative fit statistics, we need 2 different models to compare. So if you remember, the theory behind the BFI dataset recommended 5 factors, while the eigenvalues recommended 6. And we're going to set up the 2 models by changing the n factors argument. And when we're looking at BICs, the lowest BIC is always preferred. And you can see that for these 2 models, the BIC is lower for the BFI underscore eigen model, which was estimated to have 6 factors. And just to conclude, when you're in the process of developing your model, the first initial step is to make sure your model or the models have adequate fit according to absolute fit statistics. If you're comparing multiple models that all have good fit, you can use relative fit statistics to make an empirical determination about which model is mathematically preferred. Let's go through our tutorial in R. We're going to select the best model using the knowledge of finding and interpreting absolute and relative model fit statistics to select the best model for the data. When I introduced this data set, I said that the items were theorized to load onto 5 factors, but you may have noticed that your scree plot indicated 6. You might be wondering which you should trust. And this is where we use fit statistics to make an empirical decision about how many factors to use. First, we're going to use the BFI underscore EFA data set to run EFAs with each of the hypothesized number of factors. Then we're going to look at the BIC, which is a relative fit statistic to compare models. Remember, lower BIC is preferred. So let us run each theorized EFA on the data set. And here, we're just going to call it the theory version. So BFI underscore theory, and that's going to be a factor analysis of BFI underscore EFA, and we're going to use the number of factors equal to 5, just like the big 5 factor model. But then we're going to use the one that we obtained from our data, which is the BFI underscore eigen, and we're going to run a factor analysis on BFI underscore EFA again. However, this time we're going to use 6 factors, just like our scree plot told us. When I run that, just stored right now, the last thing I need to do is compare the BIC values. So I'm going to compare the BIC values. So I'm going to have BFI underscore theory, $. What do I want from there? I want the BIC. Boom. And then I'll do the same thing for the eigens. So we see here that the lower BIC is part of the eigen data set. There are other type of values we could compare. If you saw when I brought it up, I went BIC underscore theory, BFI underscore theory, $RMSEA, so I can get those values. This is a weak RMSEA, looks like above 0.05, but 0.06 is acceptable based on class rules. Let's see what it looks like for the eigen. Lower than 0.05. So far, I'm liking the eigen model. If I do the same thing again, let's do it with TLI. Let's see if that works. TLI. It works. TLI. Here we can clearly see that the 6-factor model is better than the theorized model. And that's going to be the end of our tutorial of exploratory factor analysis.